Have you ever, really looked closely at the fabric of the shirt you're wearing? It seems so simple, right? But it's actually an incredible grid of thousands of threads, all perfectly interlaced. So how on earth does that happen? Well, it turns out it's an amazing story of hidden geometry and some seriously brilliant mechanical engineering. Let's unravel. So here's our roadmap. First, we're going to tackle the basic weaving puzzle. Then we'll zoom in on the geometry of something called the shed. After that, we'll meet the real star of the show, the cam. We'll see how its shape dictates the pattern, why a smooth motion makes for better fabric, and finally, we'll uncover the hidden efficiency in its curve.
All right, let's dive right in with the most fundamental problem in modern, high-speed weaving.
Really think about that for a second. How do you get thousands of vertical threads to go over and under thousands of horizontal threads, thousands of times a minute, without the whole thing just tangling up and breaking? Well, the answer is in one primary, really elegant motion. And that motion is called shedding. All it is the action of separating the long vertical threads, those are the warp threads, into two distinct layers, a top one and a bottom one. This creates a tiny little tunnel, and that tunnel, believe it or not, is the key to everything.
Okay, so you make a tunnel. But here's the thing. It's not enough to just create an opening. The exact shape, the precise geometry of that opening is absolutely critical.
And this image shows it perfectly. That triangular opening right there, that is the shed. It's the little passage where a shuttle carrying the horizontal thread, the weft, shoots through at incredible speed. Seems simple enough, right? But the precision of this shape is where the real engineering magic begins. So why does this one little triangle matter so much? Because its exact geometry controls literally everything. We're talking thread tension, friction, and whether or not your threads are going to snap. It determines the final quality and density of the fabric. You get this geometry wrong even by a little bit, and the entire operation just grinds to a halt.
So if the shed shape is that important, what's controlling it? Well, this brings us to the mechanical brain of the whole operation, a surprisingly simple device called a cam.
Now, before we see the cam itself, we got to understand the instructions it's following. For a basic plane weave, the threads need to do 4 things: rise up, then dwell, which is just a fancy word for hold still, then fall back down and dwell again. This graph is like the abstract blueprint for that entire motion.
And this is how that blueprint becomes a physical reality. The shape of this cam isn't random. It's a direct mechanical translation of that graph. You see the sloped parts of the curve? Those push the threads up and let them fall. And the perfectly circular sections? Those create the dwell periods, holding everything perfectly steady. It's basically code, written in metal.
Okay, so that's all for a simple, plain 1/1 underweave. But what happens when you want a more complex pattern, like the diagonal twill you see in a pair of jeans?
Well, the instructions have to change. On the left, there's our plane weave graph again. But look at the one on the right for a twill weave. The pattern's different, right? See how that top dwell, the part where the threads are held open, is much, much longer? That's because for this pattern, you need 2 weft threads to pass through before the shed can close.
And here is the payoff. This is how that new blueprint creates a totally different physical part. On the left, you've got the cam for the plane weave. On the right, the one for the twill. The difference is obvious. That longer dwell time from the graph translates directly into a much larger circular section on the cam itself. And this is the most important point. A different fabric pattern requires a physically different cam. But it's not just about the pattern. For weaving at high speeds and getting high quality, the way the threads move is just as important as where they move. And this is where the engineering gets truly elegant. So, when you design a cam's curve, there are 2 main approaches. The first is linear motion. It's the simplest. It just moves the threads at a constant speed. Think of it like flipping a light switch. Bam, on. Bam, off. It's abrupt. The other way is simple harmonic motion, or SHM. This is way more like gently pushing a swing. It starts slow, speeds up through the middle, and then slows down again at the end. It's smooth and gradual.
So what's wrong with the simple light switch way? Well, this graph of its speed and acceleration tells the whole story. Look at those insane vertical spikes. They represent a sudden, jerky start and stop. That shock puts a ton of stress on the threads and the machine parts. It causes vibrations, it causes breakages, and it causes a lot of wear and tear.
Now compare that to the profile for simple harmonic motion. It's night and day, isn't it? Everything is a smooth, gentle curve. The speed changes gradually. This smooth motion totally reduces that shock, which lets the loom run faster and more efficiently. And the result? A much higher quality fabric with way fewer defects. It's just a more elegant way to solve the problem.
So let's bring this all together. After this deep dive into the guts of a loom, what's the big takeaway here?
It all comes down to this. The shape of one small, spinning piece of metal is everything. That precise, calculated curve isn't just a random lump, it's a physical program. It is mechanical code that dictates the pattern, the quality, and the durability of the very fabrics we live our lives in every single day.
And thinking about that really makes you wonder, doesn't it? What other simple, elegant machines are out there, hiding in plain sight, just quietly running our world?